All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're doing another 3D one. In a previous video, we'll throw that up we'll link it. We use the cross product. We're gonna use a different method to solve out 3D rigid body equilibrium problems. In this one, we have a plate shown, has a weight of 500, and we're given that here at W, 500 pounds. It's supported by shaft AB, right here, and cable C, as shown. Our support here at A on the shaft is a journal bearing. Our shaft at B is a thrust bearing. A journal bearing should allow our shaft to slide through it. A thrust bearing prevents that motion from happening. But either way, we can rotate in there. Basically, at B, we will resist force in the X, Y, and Z directions. At A, we're only going to resist force perpendicular to the shaft. If all we had was A, that shaft can move parallel to the shaft or in the X direction for how this one was set up. But for this method, if we're not using the cross product for everything, we're just going to come in and try to directly apply moment is force times distance for anything. If we're doing that, when we get to moments, we're going to need to remember if a force is parallel to or passes through an axis. It will cause no moment about that axis. It causes no moment about that axis. So for example, if a force is parallel to the z-axis, it won't cause moment about the z-axis. So like F2 here, straight up and down, we'll get no moment about that axis, the z-axis. If we pass through, if the line of action intercepts the z-axis, or the x-axis, or the y-axis, we're not going to get moment about that given axis either. So we'll have to assess this as we actually tackle our moment pieces in here. Also, just one other kind of general note in here. With my poor drawing skills, it's hard to tell. B is supposed to be the origin on this. The x, y, and z axes all intercept right here at that support at point B. It's hard to tell if B is 0.5 meter or feet away from the origin or at the origin. It is the origin, is what we're trying to show in here. That 0.5 foot distance is from B to the plate, is what we're trying to show with that. So just trying to clear up my drawing skills. Let's just jump in and start applying equilibrium equations. We go directly for it on this one. So I could come in and say, let's sum forces in the x to start this one out. So if I sum my forces in the x direction, this is going to get me, actually before we do that, let's make our free body diagram. Should be our first step in here. I'm going to have, I have my picture, I have the general drawing laid out down below. Let's just start working through that. I have F1 goes straight down here, 300. And I have a cable that's holding it up. That's going straight up on this one. So going straight up, I have some tension, and I'm just going to call that T for tension. I also can put in here at the back right corner of my plate, I have F2 coming down. So that should be right about here, or right about here. I would have my F2 was given as 400 pounds. So 400 coming down there. At the center of our plate, I have the weight and F3. Weight going straight down in the negative z direction. We're told the weight was 500 pounds, so let's fill that in, 500. And entirely, this looks like it's going entirely in the y direction. We're not giving anything that says it's not. So we'll go ahead and assume that is entirely in the y. Our F3, 600 pounds, parallel to our y-axis. Something like that. That is 600. Then we just need our unknowns. At A, we have a journal bearing. Journal bearings resist force perpendicular to our shaft. That would be in the y direction. Y. And our z direction. So I have an AY and an AZ. Out here at B, we have our thrust bearing. So I should have forces parallel and perpendicular to our shaft that we're resisting. So just like before, we'd have that BY, and a BZ on this. BZ. It's the same as our journal bearing. We're just adding in that one parallel force in here, a BX. For a total of 6 unknowns. AY, AZ, BX, BY, BZ, and our tension T, 6 unknowns. I have 6 equilibrium equations. I can tackle these. Also in 3D, my general approach is assume everything in the positive direction if I don't have a strong reason to do something different. So that's how we set everything up here. Let's come into our force equations. I can sum forces in the X. All I have in the X direction right now is BX. Summing force in the X equals BX, which has to get us to 0. Or BX is 0. And technically that is one of our equations. That's equation, we'll number it off. That's equation number 1. I'm going to end up needing to make a system of equations here. Even though that one's solved, I'll still count it in my numbering. Then let's come in sum forces in the Y. Summing forces in the Y direction. I have, I have an AY, so AY. I have BY plus BY, and I have 600 plus 600. And that's it for us. This equation, obviously, one of these has to have the wrong sign on it. It's actually going the negative direction because all 3 of these are positive. That can't get us to 0. We're not going to worry about that, though. Just leave it as is. Set the whole thing equal to 0. That's all the farther I can really go with that. Let's call that equation 2. Equation 2. And then finally, I can sum forces in the Z direction. Is my third force equation. Summing my forces in the Z direction, I have all my Z components of force. I have an AZ. I have a BZ plus BZ. I have an unknown T plus T. I have F1 coming down, minus 300. I have F2 coming down, minus 400. And I have the weight coming down, minus 500. And that has to all add up and get me to 0. Equals 0. I'm going to reduce and simplify this one a little bit rather than having 3 constants in here. 500 plus 400 plus 300 is 1,200. Let's just move it to the other side. We would get AZ plus BZ plus T equals 1,200. And that's going to be my third equation, 3, that I'm setting up in here. That's equation 3. We're hitting the picture there. But equation 3. I have 3 equations. I have way more unknowns than that. So I can't solve anything else out at this point. Let's go in and start trying to do our moment equilibrium. So for this approach, we're just going to sum moments about our given axes, X, Y, and Z on this. As we're doing that, we're going to need to say our moments, and this is where this gets a little bit tricky. We have to be able to wrap our head around it. A ton of people just struggle visualizing what's going on. If that's you, just use the cross product approach. We're going to say our moment or our force will be positive if it causes a counterclockwise rotation about an axis. But that depends on which end of the axis are we looking at. So we're going to have to say if we are, I pretend that I'm standing on the positive end of my axis, looking back towards the origin. Or kind of I could draw in like an eyeball here. That's my eyeball. We are looking from here back towards the origin. If our force looks like it's causing a counterclockwise rotation, it's positive. Otherwise, we'll put it as a negative moment. And we can do that on all of our axes. Down here at our x-axis, we would swing down and under the axis, come up, over, and around. Will be our positive, and that's if I'm standing out here on the x, looking back with my eye towards the origin of this, on my eyeball symbol. Or same thing for Z. If I am floating up here at the Z, it should look like I'm getting a counterclockwise rotation about my Z-axis. So doing something kind of like this. I accidentally closed my circle out there. Something kind of like this. And that's again if I'm standing up here at the Z, looking back down towards the origin for everything in there. There's our eyeball symbol. We're looking there, going down towards the origin. We got to be able to wrap our head around that for this method to work. Otherwise, we're just guessing blindly on rotation directions, and it doesn't work well. So if this doesn't work for you, use the cross product. If this works, it's a little bit easier to kind of just, force times distance. There's less like the tedious calculations for cross product that we have to do. But let's come in and try to do this. So we're going to come in and start applying our equations in here. I'm going to do a moment about the x-axis first. Summing my moments about the x-axis. So we'll take a look at force times distance to every single force in here. If we go parallel to the x-axis, or if the line of action passes through the x-axis, we'll get no moment in here. So I want to include them. So let's come in and try to work through this. So for F1, going straight down here, that would go behind the x-axis. It's going to miss it by 3 feet. So this one would have to be included in here. If we could only rotate about the x-axis, and all that I did was pull down on the back corner of this, we would swing down under the x, up and around. It would look like we were standing right here, like it's going counterclockwise. So this is positive for us. My F1 is 300. Force times distance, 3. We can also get to, we'll get F2 in here, would also be positive. It's also 3 feet away. So plus force 400 times distance 3. We can get F3 in here. If I am right here, as I look from X back to the origin, if I pull to the right at F3, that's going to make it swing clockwise. So I need to subtract this one off. Minus my force is 600. And if that point is right in the dead center of this plate, which we know it is because that's where the weight's at, then it should be halfway in the X direction, halfway in the Z direction up. I can take that Z direction for my moment for this one. So half of my dimension is 4. Half of 4 would get me a distance of 2. Times 2. That same idea would be true for our weight. The weight would cause a positive rotation. So plus my weight is 500 times our distance would be halfway in that Y dimension. Half of 3 is 1.5 times 1.5. And our final unknown is my tension in here. That tension, if our F1 and F2 cause positive, tension would be clockwise, so negative, minus 3t equals 0. I can solve that for my tension, and I'm going to get that my tension here is 550 pounds. And that's another answer for us. Technically, we could also come in here and say, that's my fourth equation I've set up. I just been able to simplify it all the way down to get an answer out. So mark that. That is equation number 4 that I'm working with there. Then I can go on and keep doing additional equations. Let's sum moments about my y-axis. Summing moments about the y-axis. So this time I'm referencing the y right here. If I'm parallel or passing through y, we don't need to include it. Also, I should have mentioned, I didn't include bx, by, bz. They all intercept the z-axis, so I don't include them in here. That same thing is going to be true for our y-axis. bx, by, bz, if they pass through the origin, they're intercepting every axis, so they won't show up in any of our equations in here, and that's okay for us. I didn't include az and ay up in this equation because these are both intercepting the x-axis as well. So let's go ahead and do this for the y-axis. We can start out and say, well, if I look at A first, AY, that's going parallel to Y, so I don't include that. AZ, that one doesn't go parallel to the Y-axis. It also doesn't intercept it. So I'll have to include that in here. If I'm standing right here looking at the origin, AZ is going to make this look like it lifts up and swings clockwise around the Y-axis. So that's going to be a negative moment. Negative, my force should be AZ, and my distance is 0.5 plus 3 plus 0.5, negative 4 AZ. Then we can go to B. We already said B doesn't cause any moment here because they all intercept. So let's go to our tension. That tension would also cause a negative moment on here. So minus, our distance would be 0.5 plus 3 gets us to where T is located. So minus 3.5 distance times tension, 550. And then we can come in and say, what about our next ones? Well, that 300, it will be included in here. It's just opposite of T, so we'll add it. Plus, my force is 300 times my distance is 3.5. We also need to get in our 400-pound force plus force is 400. It would cause a counterclockwise rotation, so we're adding it. And our distance here is just 0.5 times 0.5. Our last thing that we need to get in here is what's going on at the center of this plate. We have the weight and F3. Well, F3 goes entirely in the Y direction. That means it's parallel to Y. We don't include it. I just need the weight in here. It would look like it's causing a counterclockwise swing, so we'll add this in. Plus weight 500 times our X distance. Well, if it's in the middle, that'd be from the middle to the edge of the plate is half of the width of the plate, 1.5, plus that additional 0.5 to get to B times 2. That's everything causing rotation here. So that is equal to 0. AZ is my only unknown in here. I can get the AZ is equal to 81.25 pounds, which would be another answer for us. That was my fifth equation I set up. Even though I fully solved it right there, I'm still going to label that as equation 5. Just so I can make sure as I'm counting this off, there's a lot of work that goes into it. Have I actually done 5 equations? I have one equation left. I haven't done moments about the z-axis yet. Let's tackle that one. Summing our moments about the z-axis is going to get me, well, if I'm parallel to z or pass through the z-axis, I have to include it in here. So let's start at A. At A, AZ goes parallel to the z-axis. I'll include AY. It would look like it's causing a counterclockwise rotation. It is 0.5 plus 3 plus 0.5 for AY. At B, all 3 of my forces intercept the z-axis, so I won't include them in this. I can go to, a lot of these actually don't show up in here. At this corner, T goes parallel to Z, F1 goes parallel to Z. F2, straight down, parallel to Z. The weight, straight down, parallel to Z. Really, the only thing I have in here is this F3. I have to include that. If I pull here, it would look like it's going counterclockwise, so we'll add it in, plus my force is F3 600 times my distance, 0.5 to get from B to the edge of the plate, and then half the width of the plate, 0.5 plus 1.5 is 2. Or solving that for AY, because we know this equals 0, we're going to get here that AY is negative 300 pounds. Should be another answer for us. And I use 6 equations at this point. That's equation number 6. So I should be able to use between my unsolved equations 2 and 3 and the 4 that I solved out, I should be able to get my final unknowns found. So I could take what I get for equation 6, let's plug that into equation 2. So I'm going to say I'm doing 6 into 2. AY, negative 300, plus BY, that's unknown for us, plus BY, plus 600 equals 0. Equals 0. Or BY works out to be negative 300. BY is negative 300 pounds, which is our second to last answer. From here, the last step, I could just take what I have for equations 4 and 5 and put them into 3. I have A, Z, and T. B, Z would be my only unknown. So 4 and 5. 4 and 5. And I'm plugging those into 3. This is going to get me AZ, 81.25. 81.25. Plus BZ, which I don't know. Plus BZ. Plus T, I know T is 550. Plus 550. Minus, or not minus, equals 1,200. Equals 1,200. Moving that 81.25 and 550 over, I'm going to get here my final answer. BZ is equal to 568.75. 568.75 pounds. Which would be my final answer for everything. But again, we can kind of slow and steady through these ones. This approach takes more conceptualization. We have to wrap our head around it, figure out these rotation directions. That can be really tricky to do, actually. But if we can, these become an easier approach than doing the cross product. The cross product is actually really straightforward. There's just so many opportunities for us to make like a single sign error, and it gets really annoying then. But either way, we should get to the same final answer. Also, I'll be upfront with you. We largely don't go on and do much with 3D particle equilibrium. If this is just, or not particle, rigid body equilibrium, if this is terrible for you, do your best with it. I'm not going to put this on a test for my students. I bet that your professor doesn't do the same. Don't quote me on that because they probably will do it now that I said that they won't. But my guess is there's more important things that they could test on. So don't stress out. This isn't the end-all thing. If you can do 2D rigid body equilibrium and can't do this, you're probably still looking great in statics. Don't stress out about it too much. This becomes a huge algebra challenge more than a huge statics challenge. But hopefully this was a useful video for you. If it was, hit those like and subscribe buttons. Stick around. Let's get you an A with JJ.